Hi everyone, in this video I'm taking a look at question 11 part C of the 2020 Extension 1 trial exam from James Ruse. So it's a 3-part question, so as usual I'll work through each part in a separate video. In this video I'll be focusing on part 1, which tells us to express 3 cos theta plus 4 sin theta in the form r cos theta minus alpha, where r is greater than 0 and alpha is between 0 and pi on 2. So let's take a look. So I've written out what we're being asked to do, which is to express this sum of 2 trig functions. So we've got 3 cos theta plus 4 sin theta, and we want to combine those into just one cosine. And the idea is that effectively the cos or the cosine curve and the sine curve, they're effectively the same curve, they're just offset. And so if you were to add them up, you'll in effect get once again the same shape, just with a different amplitude that we're going to call r, and a different offset that we're going to call alpha. So it's possible to find a value for r and alpha that effectively gives you the identical curve. And you could actually pick the sine curve here if you wanted, and you could have a positive or negative alpha. Either way, you'll just get slightly different results for what r and alpha should be. But in this question we're told that we want cos or cosine as the aggregated function, and so basically the method we're going to use, it's often referred to as the auxiliary angle method. The idea is that we can expand this cos theta minus alpha, and then we can effectively equate coefficients. So maybe we'll start with that. So we'll start with r cos theta minus alpha, and we can expand that as r times, and then we use our rules for the cos of a minus b, where here we've got a as theta and b as alpha. So cos of a minus b would be the cos of a cos of b, so for us it would be cos of theta cos of alpha, and then we get plus, and then it's the sine of a sine of b, so for us it would be sine of theta sine of alpha. And then the next step would be to expand this r. Now what I might do, because over here what we're being asked to express in a new form is something times cos theta plus something times sine theta, it would be nice to have the same form, because here in this format alpha is just a constant, so the cos of alpha is just a constant, same with the sine of alpha. So we'll put our constants out the front. So we'll have r cos alpha cos theta plus r sine alpha sine theta. And then it's really clear how we can now equate the coefficient here, 3, with our coefficient here, r cos alpha, and then our coefficient 4 with our coefficient r sine alpha. So that's the next step. So maybe I'll say, therefore, by equating coefficients, what we get is we'll get r cos alpha will be equal to 3, and we'll also get r sine alpha will be equal to 4. And then the key here is to work out what r and alpha should be. We have 2 equations and we have 2 unknowns, so it's easy enough to do. Often the cleanest way to go about it is to try and get a sine squared alpha plus cos squared alpha, knowing that that's equal to 1. So I guess a straightforward way to do that would be to square everything. So here we'd get r squared cos squared alpha equals 3 squared, which is 9. And we get r squared sine squared alpha would be 4 squared, which is 16. And now we can add up these 2 equations. So therefore we can say r squared cos squared alpha plus r squared sine squared alpha would be 9 plus 16. And so if I factor out my r squared, we'll get r squared times cos squared alpha plus sine squared alpha, and that's going to be 9 plus 16 is 25. And now we've got a cos squared alpha plus sine squared alpha, so we know this is 1. So we simply get r squared is equal to 25. And then we get r is the square root of 25, which is plus or minus 5. But we only need to take the positive, and we can do that since we know that r is greater than 0, because that's what we're told in the question. So now that we've got r, we can plug that back into either of these two equations to then solve for alpha. So I'll just might as well take this first one here. So therefore we can say that 5 cos alpha is equal to 3. So cos alpha is equal to 3 on 5. So alpha is equal to the inverse cos of 3 on 5. And if you were to stop there, that would be fine in terms of alpha. You've got that in a perfectly precise form. But if you wanted to, you could throw that into the calculator. So I'll just get out my calculator here. And if I go inverse cos of 3 on 5, we'll get 53.13, and that's in degrees. So I could write that as 53 degrees and I'll call that 8 minutes, we could say. Or we could, if we want, write it in radians. It's quite common in say, extension 1 and extension 2 in particular, to think about angles in radians. So I could divide this by 180, and it would be 0.295 and so on pi. Or if we wanted to, we could actually multiply by the pi, so times pi. And as a decimal, as a pure decimal, we get 0.927 and so on. And given this is a multi-part question, it might be worth actually saving that to memory just in case the exact answer we need to make use of later in terms of alpha, just to save us having to rekey the inverse cos of 3 on 5 every time. So that gives us r and alpha. So now we can, I guess, make our final statement for this question. We can say, therefore, 3 cos theta plus 4 sine theta can be written as 5 times the cos of theta minus alpha. And you could, in theory, write either of these forms. You've got 4 options. I might just pick the most precise form. So the inverse cos of 3 on 5. Boom! And that's how you tackle that first part of that question. So hopefully that makes sense. It's basically making use of the auxiliary angle method. And the key to it is knowing how to expand this cos theta minus alpha and then equating coefficients. And everything falls out pretty nicely from there. So hopefully that makes sense. And what I'll do in the next video is I'll take a look at part 2 of this question. All right, tick boom.